the robot and the lasers is totally accurate. I'm trying to do these experiments in an automated fashion and completely optically, which is something that 8 years ago would have been rightfully considered pure science fiction. And so the amount of technology that we have now that we didn't not so long ago is really staggering. And my goal in presenting my work is to try and communicate the awe that I have of our actual capabilities, as opposed to trying to make these sort of general sweeping claims that gloss over the details. And I was particularly peeved by this headline that came out recently that says Canadian scientists create first functioning virtual brain, when the actual thing that they did, which is very cool, is that they created a neural network that can solve more than one task, whereas previously neural nets could only be trained to do one thing at a time. And neural nets are experiencing this really interesting renaissance, where for a long time it was considered neural nets were a dead end. They weren't really useful for anything. They certainly didn't resemble actual nervous systems. And now we have deep belief nets, and we have these interesting systems like Spawn, the one that headline was about, where you can organize neural nets to share different pieces so that they can accomplish different tasks, but also exchange their learnings with each other. So there's a lot of interesting things happening in neural nets, but instead everyone writes about it as though we've solved the brain now. And so I want to talk about some of the really fascinating technologies that have recently come out, like two-photon digital holography. And I just think it's crazy that there is an actual thing that happens that's special when two laser beams meet each other. It is a sort of this fantasy that you have, where like, oh, when two lasers cross, it's like lightsabers. And something special happens in the middle. And actually, if you take two lasers, generally nothing interesting happens. It's quite disappointing. But if the lasers are sufficiently fast, if you're using femtosecond pulses, then the amount of photon flux at the point where the beams meet can actually reach a sufficient level to cause these two-photon events, where two photons from either side actually arrive at a single molecule at a single instant, so that the electron does not have time to decay after encountering the first photon before the second photon shows up, and it's as if a single photon of twice the energy had arrived. And that doesn't happen anywhere in the surrounding space. It only happens where the photon flux crosses this two-photon threshold. And so you can use that to cause effects in a three-dimensional sample where they only occur at a single point or a single set of points, and not in the surrounding neighborhoods. And so this is a critical technology for stimulating an individual neuron by computer control in a three-dimensional nervous system, as all living nervous systems are, and we're not talking about slices. So that's a cool thing. It's a cool thing that we have, like InfiniBand RDMA, which can combine individual computers into a supercomputer in a way that we couldn't before. And that sounds very hyperbolic, because saying, oh, we have supercomputers. And of course, we've had supercomputers for a long time, and you can always network computers, and you can do distributed computing. But the cool thing is it's reduced the latency. So you no longer have to do an act of communication. Which actually kind of goes back to what Ben was saying, where you take your data packet, you format it into internet protocol, and exchange it across a network, and then it's received at the other end. Now with InfiniBand, you can have RDMA means remote direct memory access. So one computer can directly access the memory in a remote computer. We couldn't do that before. That's really cool. And that enables a new class of applications, very high throughput image processing, for instance, that are necessary for what I'm doing. There's also we have good jitting compilers now. This just crossed the threshold a few weeks ago, and it sort of made quiet news in the computer science community. It showed up at maybe number 20 on the front page of Hacker News, and that was about all there was to it. People talk about self-modifying code in Lisp, for example, but the Lisp macro system takes place when you're actually compiling the code. So at a single step, after you've written down your expression, the compiler can run your code on itself, translate it into a form that is more detailed, so that you can be more poetic and expressive in your Lisp coding. This is extremely powerful, and people rightfully talk about how great Lisp is, because you can do this sort of macro coding. But once you've done it, once the program is running, all you have is eval, which is cumbersome and slow. You can create code and you can run it, but it costs a huge amount of overhead. And so it's not really self-modifying code in the sense that as it experiences the world, it can adapt to changing circumstances. It's only self-modifying in the sense that you're writing a program to write the program for you. But we've actually gone through that limit now. LuaJIT 2 is the name of the thing. And I think this is really important. It's now, with almost zero overhead, you can generate code on the fly that runs at native speeds. So that's another thing that I'm using in my machine learning system. So there's all these really cool things, and I'm just trying to express that. And the way I'm doing that is through hypertext. So I have a web page for Nemaload where I give a very short overview of the project, but all of the fancy words like transgenics and 2-photon and holography are all hyperlinks, and then I try to explain each of these new technologies and how they work with each other, and how they can be used to produce this one single result that draws on a number of different fields. So basically, my message is when we're writing about the future, we shouldn't be scared to be concrete about the actual capabilities that we have and what the actual factors are. What are the limiting factors that are removed by each new innovation? What are the new things that we can do that are not just interesting steps towards some abstract future, but actual capabilities that we now can take into our hands and apply to problems now. Like understanding the simplest brain, which, I mean, understanding how the nematode thinks. It's 302 neurons. It's very simple. Its most interesting behavior is that it likes to be at the same temperature that it was raised at. Okay? This is not a very smart creature, but it's still miraculous that 302 neurons can produce all the behaviors that it does. It's sensitive to a number of odorants. It locomotes. It can, navigate to whatever kind of temperature or chemical concentration it wants. It's sensitive to light. It's sensitive to touch. It turns around if you tap it on the head. It does all these things, and we don't understand how it works. And nature has organized these computations in some way. And so we don't even need to talk about cortex to talk about the mysteries of brain computation. Even the very simplest brains that have nothing resembling cortex still hold interesting secrets, and we're reaching the point where we can begin to unlock those, where we can begin to look at what's going on. The big quote that I have on the front of my website is from Richard Feynman, and he was talking about the electron microscope, which came to fruition during the course of his career. And he said, in his talk, there's plenty of room at the bottom, he said, all of these fundamental biological questions are going to be very easy to answer when you can just look at the thing. And new tools for looking at things are really important. You can then look at them and see how they work. And you can use those insights to build your own copies, your own versions of those systems. So I can say a little bit more about also my background, how I came to be working on this project. Because another big part of my mission in doing this is to show that there are different ways to pursue research. So I was sort of originally an artificial intelligence student at the MIT Center for Bits and Atoms. And I was working on a computing architecture which is based on cellular automata, which is a really horrible idea. If anyone is thinking about cellular automata computing, just don't go there. It's just not very practical. It's fun to